Hello guys, Ajananjam Islam here and welcome back to lecture 3. This is the third part of this lecture and hopefully this is going to be the last installment in this topic. Of course, unless I decide to make more videos on this, in that case this is not going to be the last one. Anyway, so we have been talking about matrix transformations and linear transformations, and so far we have established two things: that multiplying with a matrix will result in a transformation, and that transformation is going to be a linear transformation. Now we know two properties of linear transformations as well. If T is a linear transformation, then it will follow the two properties. The summation will be consistent, so the summation of two elements and then taking the transformation of it will match with taking the transformations of each element and then summing it. And similarly, the scalar multiplication will be consistent, so the scalar multiplication of some element and then taking the transformation of that multiplied element will give you the same result as taking the transformation first and then multiplying the whole transformation with the same scalar factor. Now these properties are good for a number of cases, especially when you are trying to prove that some transformation is linear and when you are dealing with numbers, but these properties don't really help us much in terms of visualization. Say, we can't see what is happening when a matrix is transforming a space using these two properties. They're not very intuitive or easy to picture. So what we can do is we can derive a couple of new properties from these two. So those two properties are: a transformation is going to be linear only if the transformation will not move the origin point from its place. The origin point is the 0 point. For two-dimensional space, it is the 0, 0 point, and for three-dimensional space, it is the 0, 0, 0 point, and so on. The second property is all straight lines will remain straight. So after you apply the transformation, when the space is transformed into something else, a straight line that was straight before will remain straight afterwards. And in other words, we can state the same property by saying that the grid lines, that is the lines parallel to x and y axis, and when we are in higher dimensions, z axis and other axes, they will all remain parallel and evenly spaced. If they are not parallel and evenly spaced, straight lines, all the straight lines cannot remain straight. So these two are saying basically the same thing. So in light of these two new properties that we derived from our two old properties, we can say that this is a linear transformation because the origin is in its place, and although the y-axis has become slanted, the lines parallel to y-axis are still parallel and evenly spaced, so the distance from here to here is the same as the direction from here to here. But this transformation here is not linear. The lines are still parallel and evenly spaced, straight lines are straight, but the origin has moved from its place. So this is a violation of one of our properties. Similarly, this is not a linear transformation because the origin also remains in its place, but all the straight lines have become curvy and, messy. So these two new properties of linear transformations are much more helpful for visualizing a transformation and whether or not a transformation is linear. Luckily, every matrix transformation is linear, as we saw in our last lecture, so we don't really have to worry about this too much. So let's update our list of what we know. We know that multiplying a vector with a matrix causes a transformation. We know that a space is made of a lot of vectors. A space is basically a collection of vectors. And when we multiply the matrix with all of those vectors, we basically transform the whole space into something new. We also know that these transformations are always going to be linear in nature when I'm multiplying with a matrix. We have proved that in our last lecture. And fourthly, linear transformations are going to keep the origin in place, and the grid lines are going to be parallel and evenly spaced. I hope all of these are clear, and looking at this, you can see what they mean. So we can move on. And we have to move on because we have two more important questions to answer. And those questions are, let's say I have a matrix. How am I going to realize what this matrix does? Now, yes, of course I can just multiply it, but that will just give me two numbers. But what just happened? What are these two numbers? Is the transformation matrix rotating the space? Is it causing a skew or a shear? Is it scaling the space into something new? We don't know. Just multiplying the matrix will not give us the answer. We need to have a better insight, and we don't know how to do that yet. The second question is, let's say we have a certain task at hand. So we have a vector x and y. We want to rotate it by 25 degrees. So basically what I'm saying is, I want to rotate a vector 25 degrees or by some other degree, doesn't matter. In this example, we are rotating at 25 degrees. I don't know what matrix will get the job done. What are going to be the numbers here that will achieve the desired results? I don't know. So those are two answers I'm going to find out. And luckily, those two answers are very straightforward and pretty interesting. So this is a two-dimensional. We are working on two-dimensional vectors because that's the most easiest way to plot and show you the things. But please remember that all of these apply to any of the higher dimension as well. It works for 3-dimension, 4-dimension, n-dimension. So for now, we are in a two-dimensional space. We have a vector, and we know that every vector is basically a linear combination of the basis vectors, right? So this vector right here is actually 4 into I hat and 3 into j hat. But we also know that linear transformation will preserve the linear combination. So if V, let's call this V, if this vector is a linear combination of the two vectors I hat and j hat, then the transformation of the vector V is going to be the same linear combination of the transformation of I hat and the transformation of j hat, because this is the definition of linear transformations, right? So if I apply the transformation on this vector, the linear combination property will still hold. The only difference is it is not going to be I hat anymore. This is 4 into this vector. This vector is obviously not I hat, plus 3 into this vector. This vector is obviously not j hat. But the linear combination property still holds. This transformed vector is going to be 4 into this vector plus 3 into this vector. And this is true for any sort of linear transformation. If I do a skew, this vector is still going to be 4 of this vector plus 3 of this vector, right? So what are these vectors? This not I hat and not j hat vector. What are these vectors? Well, these are simply the transformation of I hat and j hat. The same transformation that got our vector from some other place to this place got our I hat vector to here and our j hat vector to here. So to keep track of what a linear transformation is actually doing, all we have to do is to keep track of the I hat and j hat vector. We have to know where they end up using the same transformation. So for example, this matrix, we have a matrix here. I don't know what it does, but if I can find out what it does to our basis vectors, I'll find out the answer. So we have our I hat vector. If I multiply it, we get 1, 0, nothing changes, so our I hat vector doesn't change. We have our j hat vector, and if I multiply it with this matrix, this is going to be 0, minus 1, so our j hat vector will come from here. So look at this, the x-axis does not change, but the y-axis flips over. There is a vertical flip along the y-axis, and also important to note, the length of either I hat or j hat does not change, which means there is no scaling involved. All we are doing is keeping the x-axis as it was and flipping the y-axis to the opposite direction. So let's apply this knowledge to some other vector and see if we are right. So this is our vector. We are going to multiply it with this matrix. According to what we have seen, the x-axis should be same because there has been no change along the x-axis. But the y-axis is going to flip over. So this vector will just flip along the y-axis. So, or you can say this is being reflected across the x-axis. So if this is our reflection surface, the vector is coming from here and being reflected across the x-axis. Or you can say a vertical flip. Both means the same thing. So as you can see, the information we got from the basis vectors are consistent. Yes, all the vectors are actually being flipped over along the y-axis. Unfortunately, when we have a matrix, figuring out where the I hat and the j hat and for higher dimension the k hat and other basis vectors land is very simple, because when I multiply a matrix with I hat, the answer is the first column. It's always going to be the first column. When I multiply the same matrix with j hat, the answer is always going to be the second column. And this is true for any dimension. For example, if you have a three-dimensional matrix, multiplying with I hat will give you the first column, multiplying with j hat give you the second column, and with k hat will give you the third column. So it's pretty easy. Just by looking at a matrix, you can see where the basis vectors will land. All the columns will give you the answer straight away. Now, let's see a couple of examples and test our theory. So, we have a matrix. We want to know what this matrix does. So the first column is telling me that the I hat vector is going to land on -1 0. So the I hat vector is currently on 1 0 position. This is our 1 0 position. It is going to fall on -1 0, right? Which is given by the first column here. So our I hat vector is going to come here. The j hat vector is going from 0 1 position to 0 -2 position, which means I'm going to have a horizontal flip because the I hat vector has gone from this position and flipped over to this position. So a horizontal flip and also a vertical flip, but the point to notice here that the vertical flip is associated with a scaling because our vector has gone from 1 unit length to 2 unit length. So the y-axis is not only flipping over, it is also being scaled by a factor of 2. Let's take another vector and see if it works. So this is our vector 2, 1. If we multiply it with this matrix, we have a horizontal flip. We also have a vertical flip with the y component being doubled. So as you can see, our theory is correct. We were from here, we have been flipped horizontally and then vertically, but with the vertical flip there was a scaling factor, so we have come to the point -2, -2. Now for the second example, we are going to come from the other way. Let's say we have a certain transformation in our mind. We want to rotate the whole space 90 degrees counterclockwise. What matrix will get the job done? What I want is the space to rotate 90 degrees counterclockwise, which means both basis vectors will have to rotate 90 degrees counterclockwise. So j hat will have to go from here to here, and this position is the -1 0 position. So our second column, which gives us the transform position of j hat, has to be -1 0. Similarly, I hat vector will have to go from here to here, which is the 0 1 position. So the first column, which gives us the transformed position of I hat, will have to be 0 1. Now multiply this matrix with any vector and see if it works. Every vector is going to be transformed such a way that the vector is going to be rotated 90 degrees. Every vector in the two-dimensional space. Pretty neat, right? Now you have a better understanding of what matrices do, and also if you are anything like me, I think you have a newfound respect for matrices. They are not just a bunch of numbers, they are very powerful. Anyway, we are going to stop here for today. I have a feeling this is not going to be the last video on this topic because I want to show you a couple of ways how you can use this knowledge and how cool the effects can be. Until then, goodbye.